Hello everyone. In this video, I'm going to provide the details how to derive finite difference discretization schemes from Taylor series expansion. I'm going to start with a very general example. Assume that we have a function f and a fixed point xi. So we want to approximate the solution which is delta x away from the fixed point. So it can be the function value at xi plus delta x can be approximated as a function value as fxi plus the first derivative ff at point I times the delta x plus half of second derivative of f at point I times the square root of delta x and plus 1/3 third order derivative of f at point I times delta x cubic. And we extend the terms to higher order for better accuracy and include more modes. For example, we want to form a finite difference discretization scheme to approximate the function value at a point using its neighboring point. This is the basic idea of finite difference. So for example, we have a 1D problem and the points which is grid through the spatial discretization is A, B, C, D, E. Assume that the distance from A to B is delta x over 3, and for the other distance, for example, B to C, C to D, D to E, the distance are uniform. So that delta x, and delta x. So for the function value at B point, we can write it as fb equals to fa plus the first derivative of f at point A times delta x over 3. Basically, we are writing based on the Taylor series expansion here. So the third term is half second order derivative of f at point A times delta x over 3. So the third term is plus 1/2 second order derivative of f at point A times delta x over 3 squared times the error, which is a third order of delta x. Here we know the order actually is in terms of delta x over 3 cubic. But if we take out the q, this is a constant. Constant is it doesn't depend on our spatial discretization. So you just remove this term, remove this 3 here. Just write it as delta s cubic. So this is the first equation. The second equation is fc for the one function value for the second equation, we try to approximate the function value at point C using the Taylor series expansion from the fixed point A, which can be written as the first order derivative at point A times 4 times delta x over 3 plus half the second order derivative at point A and their spatial distance and the error term. So we notice that we want to find the first order derivative of function f at point A. So our objective is to find the first order derivative at the fixed point A, which is this term in equation 1. And this term in equation 2. So our objective in these two equations is to cancel out the second order derivative in Taylor series expansion. Assume that we already know the function value at point B and point C. So in these two equations, how can we get the first order derivative? You can see that we need to cancel out the second order derivative terms here. So to do that, we need to use the first equation, multiply 16 and minus the second equation. So what we got is 16 times FB minus FC equals to 15 FA plus 4 times the first order derivative of f at A times delta x plus the error term. So hence we can manipulate the equation and find that the first order derivative at the fixed point A equals to 16 FB minus FC minus 15 FA over 4 times delta x. And we can find the error term is delta x cubic over delta x. So basically what we got here is a second order accurate finite difference discretization schemes. There are a few points we need to take note here. For example, we assume that the order of derivative we want to discretize using the finite difference scheme is n. So n is the order of derivative discretized with FD scheme. And we also assume P is the order of accuracy of this finite difference scheme. So is the order of accuracy of the FD scheme. So in the above equation, we notice that A equals to 2 and n equals to 1. But we can see that in the Taylor series expansion, we extend until the cubic of the delta x. So how we get there? We also further notice that 3 here is equals to n plus p. So this is a truncation order is 3. It equals to the order of derivative where we want to apply the finite difference scheme and the order of accuracy of this final finite difference scheme. So we can see here that So we assume that we already know the function values at these discrete points A, B, C, D, E, but their derivatives are unknowns. And we also know that we already extend the Taylor series expansion until the third order. So we have totally three terms on the right-hand side of those equations. Since the nodal values are known, Fa, Fe, Fc are known, and only the first order derivative and the second order derivative are unknowns. So for two unknowns, we need two equations. So the number of equation equals to the number of neighboring points. Where we need to approximate the finite discretization scheme, and we can get that for general expression, it equals to n plus p minus 1. And the 1 here, it is a fixed point. It's a point of investigation where our finite difference discretization scheme are applied to. And you can take it as a rule of thumb to plan your derivation of the FD schemes. And in the above case, the spatial discretization is non-uniform. So now we consider a special case where the mesh are uniformly discretized and we are deriving a central FD scheme. So now we consider a special case. Let's say our space are uniformly discretized with nodes, and we try to derive a central finite difference scheme, and we assume that n equals to 2 for the finite difference discretization scheme, and p, the order, equals to 2 as well. And based on our rule of thumb here, we know that the number of neighboring points equals to n plus p minus 1. So it's 3. But since we are deriving a central FD scheme, you cannot place the fixed point among the three neighboring points in the middle. So you cannot do that. So there's something fishy going on. So we will investigate the problem from p equals to 1 first. So try p equals to 1. So it's a first order accurate FD scheme. So what we have is that the neighboring points equals to 2 plus 1 minus 1 is 2. So okay, we just need two neighboring points. Like this. Here the point is I, here is J and K. We have the spatial distance delta x, and delta x is uniformly discretizing space. So for the solution U on point K, we have U x plus delta x, which is based on the Taylor series expansion equals to ux plus the first order derivative of u times delta x plus half second order derivative x squared plus 3 factorial third order derivative of u times dx cubic and plus the error term to the power of 4 why we extend so many terms in the Taylor-Series expansion for a low-order FD scheme is special here. So I'm going to explain it later on. So for the solution on point J, we have x minus delta x. So ux minus du over dx plus half second order derivative of u times dx squared minus 1 over 3 factorial third order derivative of u dx cubic plus dx to the fourth order error term. So we notice something special. Here is a third order derivative of u. You can see that this term is automatically cancelled if we plot them together. So it doesn't matter the error of accuracy, it will be always cancelled. For this term, it's always cancelled. So it doesn't affect our order of accuracy. So we are upgraded from the power of 3 order error of power of 3 to the higher order error. So the error is even smaller than our design. Once we plot these two equations together, what do we have for the second order derivative of u at point I, which is where we want to apply the finite difference scheme. We have ux plus delta x minus 2 times ux plus u x minus delta x over delta x squared. Here we have delta x to the power of 4 over delta x2. So the final order of accuracy for this central finite difference scheme within uniform mesh is upgraded to the second order. However, our original designed order of accuracy is 1. It's the first order. So it's 1 order higher than our designed. Why? It's because the cubic term is automatically cancelled in the Taylor-Series expansion. This is a special case. So whenever we apply the uniform mesh in the space, and we are applying a central scheme, central finite difference scheme, the obtained central scheme is always 1 order higher than expected. So this is a general rule when we're deriving a finite difference scheme. There are some popular finite difference schemes which we frequently encountered in simulations. It's very popular, especially in fluid dynamics and solid mechanics. So we started from the first order derivative. this first order derivative. So for central scheme, we have du over dx at point I, where we are investigating, equals to ux plus delta x minus ux minus delta x over 2 delta x plus delta x2. The order of accuracy for this central scheme of first order is second order accurate, where the original designed accuracy for this scheme is 1, so it's upgraded to the second order accurate. We approximate I in the middle of 2 points, 2 neighboring points, so we take information from all its surrounding. And the second scheme is called Euler forward FD scheme. We have du dx at point I equals to ux plus delta x minus ux over dx plus the error term. So it's first order. This is the first order accurate finite difference scheme. Basically, in this scheme, we are approximating the derivative at point I using the information from the left-hand side of its field. So it's ux plus delta x. The third scheme is Euler backward. Finite difference scheme, which is equals to UA which is equals to du over dx at point I equals to ux minus delta x over du over dx plus the error term. This is also first order accurate. So basically, we are approximating the derivative at point I using the information on the right-hand side of the computational domain. So for second order derivative, we have the central scheme as second order derivative at point I just to ux plus dx minus 2 times ux plus x minus delta x over delta x squared plus the error term. And similarly, we have the Euler forward scheme as ux plus 2 dx minus 2 times x ux plus delta x plus ux over dx squared plus the error term. And the Euler backward of this scheme, we have ux minus 2 u x minus dx plus u x minus 2 times dx over ds squared plus the arrow term. Here we notice something. When we are deriving the central finite difference schemes, the order of accuracy is always one order higher than or designed for uniform mesh, for uniform spatial discretization. And for the forward-backward finite difference scheme, for both the first order derivative and the second order derivative, we are taking the information either from the left-hand side, we can call it maybe a forward field, or the backward right-hand side, the backward field. So basically in the forward scheme, for example, for the first order derivative, we are copying the information from left to the right. And for the backward scheme, we are copying the information from right to the left. So this is particularly important for fluid dynamic problem or transient problem. For example, it's hard to apply the central scheme in temporal discretization, because you don't know what happened in future, right? You only know what going to happen from the past. So for example, this is Tn minus 1, this is Tn, this is Tn plus 1. You normally need to approximate from the Tn minus 1 to Tn. So for temporal discretization, the central scheme is normally not applied. But for the spatial discretization, and especially we are solving a fluid problem, for example, the water is flowing from the right hand side to the left hand side. So it's better to approximate the information from the downstream to the upstream, isn't it? And if the water is flowing from the left hand side to the right hand side, you'd better approximate from the forward field, from the left hand side. So you are better use the forward and finite difference schemes based on the flowing direction. So we will give more information and details how we apply this scheme in a practical way in different problems later on. And secondly, another thing we can notice that for the first order derivative, the denominator is always dx. And for the second order derivative, the denominator is always square root of delta x. And for the first order derivative, we know that n equals to 1. Assume that our designed order of accuracy is 1. So the neighboring point we need, n plus p minus 1 equals to 1. So basically in the numerator, we only need one term away from it. For the forward Euler and the backward Euler schemes. However, the central scheme is different. You cannot apply a central scheme with only one neighboring point. So you need two neighboring points, and also have to upgrade your order accuracy to 2. And same thing applies to the second order derivative. For example, we have n equals to 2 and p equals to 1. So the neighboring point is n plus p minus 1 equals to 2. So for the forward and backward schemes, you need two neighboring points here. from as a forward direction or backward direction. And for the central scheme, yes, here, since you have two neighboring points, you can place the investigated point in the middle of it. However, the order of accuracy, the final order of accuracy of this scheme, central scheme, applied in a uniform manner, is still one order higher than you expected.